Hello everyone. We can continue with the lecture 8 and I hope you can hear me. So these are the topics for today. We will continue with conditional probability. Last time I gave you a motivation for conditional probability. I will continue to give you more motivation and then I will define conditional probability and so-called chain rule. And then I will discuss a problem that can reveal a lot about conditional probability in the practical scenario. So let us continue. So this is an example that we did last time to motivate conditional probability. So here in this example, we throw two dice, A and B. So and the event is that we get an odd number on the first die. Now the question is, what is the probability of this event? So if we focus on this, then last time we did that, right? So having an odd number on the first die, so the possibilities are like 18, and then total possibilities in the sample space is 36. Okay, so the probability of the event came out to be 18 over 36, which is half. Now the question is, what if someone gives you a prior condition on what you are going to expect? Let us say some prior condition on die B, then the probability can change. So the probability it depends on the information you have in hand. So here, if someone gives me some information about the experiment, then the probability can change. So that's the idea behind conditional probability. So let us say another event is odd number on the first die, and given that even shows on die B. Okay, so now we can talk about probability like this. So let us say we have the event E, and then the condition is that even number shows on die B. Okay, so this is the probability we are talking about, and that's called conditional probability. So here some additional information is given to you on B. So hence the probability will change, because now all those cases where you had let us say 1 1 or 1 5, so these were like the odd on the second die. So these cases will be ruled out now. So your the event the set for the event changes now, given that you have someone have given you some condition on what number you can expect from die B. So these are the things. So I will do one more example with respect to die, just to clarify. So roll 2 6-sided dice, and then which yields value, let us say D1 and D2. Okay, so die 1 output is D1 and die 2 output is D2. Let E be the event that D1 plus D2 is 4. Okay, then what is probability of E? Again, like in this case, we may ask what is the sample space. So sample, since this is a two-sided die, again the sample space, order of the sample space is 36. And the event that we are given is D1 plus D2 is 4. So if we think of the event set, so what are the possibilities we have? Right? So D1 plus D2 is 4, right? So we can count those where such that D1 plus D2 is 4, since this is a small case, right? So when it can be 4, for instance, I can have 1 3, okay, or let us say I can have 2 2, okay, or I can have let us say 3 1 and so on. Okay, so similarly I can have, let us say 2 2. Well, 2 2 is already gone. So what is left here? So 3 1 2 3, and then yeah, I don't think more is left here, right? So is there anything left here? That's all we can make it to 4, right? I hope we are not missing anything here. So so the cardinality of E here is 3. Okay, so so in this case, the probability of E will be cardinality of E over the sample space S. So this comes out to be 3 over 36. Okay, so this comes out to be 1 over 12. So that would be the answer in this case. Now our goal is to look into the conditional probability case. So let us make it a conditional. So this is the same experiment where all two-sided die yielding values D1 and D2. The event is the same, where you have D1 plus D2 equals to 4. Let F be the event such that D1 is 2. Okay, now this is the condition that is given to you now, and now your probability that you are supposed to determine is probability of E. Okay, that is probability of the event that D1 plus D2 is 4, given that F is already observed. Okay, so F is observed in the sense that D1 is 2. Okay, so D1 is, you are already given that D1 is 2 now. Okay, so what will be the probability in this case, right? So earlier, yeah, it went away. So it's like 1 3, and then 2 2, okay, and then 3 1. So these were the possibilities you have for the event E. Now you are given that F has been already observed. Okay, so D2 sorry, D1 is 2 is given to you, and this is the case where D1 is 2 is there in the event, right? So in this case, the probability of the conditional will change now, right? So the probability of E given F. Okay, so a good way to write is a shortcut is E given F, right? Probability of E given F. So in this case, the probability of E given F, right? So what is left out, right? So in this case, our sample space reduced, right? So in this case, it will be 2 2. Okay, so just 1 here. Okay, so the cardinality of this set E, given that F has happened, will be 1. Okay, and so that's how your sample space will reduced here. Okay, in this case, where so in this case, the sample space will reduce. So the formula that we will, the way we will define probability of the conditional probability will be like this: E given E and F. Okay, so E and F. So this is how I will define E and F, given that F has happened, right? So this is how conditional probabilities are defined. Okay, so because since the F is already F already happened in this case, so then I will do this, right? So event E was given to me, and event F is something where it says that D1 is 2. Okay, so the F will be the event that D1 is 2. Now you have to count all those cases where D1 is 2. Okay, so that is the first output is 2, right? So first output is 2 is like there are 6 cases. So 2 1, 2 2, and 2 6. Okay, so the fact that F is given to me, so my sample space, even my obviously my how do you say, my sample space has reduced. Okay, and then I'm only looking into now relevant outcomes which are E intersection F now for me. Okay, and since event F has been observed, now my sample space now reduced, because now there is no point in taking sample space outside F because F has happened. So my sample space now reduces to F only. Okay, that is how you can think of this. And you are trying to see E given that F is observed. So only those that are now relevant with F will make sense. Okay, so you have to do E intersection F. Now E intersection F will be 2, 2. Okay, so this is like so E intersection F will be this. Okay, E intersection F, and then F we already know. So now you can now you can use this. Now you can use this to determine the probability of E given F. So now probability of E given F is how much, right? So probability of E given F is 2, comma 2. So this is over all the sample space, and this is also over all the sample space. And I'm measuring this over all the sample space. But if you think of this as a reduced sample space, then this is how it will look like. Okay, let me make it. So first compute probability of E intersection F. Okay, so what is the probability of E intersection F happening? So this is 1 over 36. Okay, and what is the probability of F happening? So it's 6 over 36, right? So this is 1 over 6. Okay, so how do we interpret this? I have one more graphics on this to explain what I'm trying to say. Why you can also have a view where sample space, you can think of this as sample space being reduced in this case. I mean, the way sample space is reduced here, you can think of this as 1 over 6 was like picking 2, 2 out of this 6 here. Okay, because only thing relevant now for me was F, because F has happened, and I am also expecting E to happen. So E, so now the only thing relevant is A intersection F. So that happens to be only 2, 2. So that's how it became 1 over 6. So 6 is the total number in the F, and then intersection from the F. Okay, and another way is like you do it this way. So you use this formula, P, probability of E intersection F over S sample space, and probability of F over S sample space. So then this is the probability, and then you divide by that. Okay, so then it comes out to be 1 over 6. Okay, so this is the idea behind conditional probability. The conditional probability tells you that if an additional information F is given to you, then the probability changes. Okay, so this is the takeaway from here. Then the probability changes, and the way you calculate is that you take the ratio P intersection F by probability of F. Okay, that's the way to compute P, probability of E given F. Okay, so okay, let me do a couple of, I can already define conditional probability like I gave you some intuition before. So the way conditional probability is denoted is this: probability of E given F. So the conditional probability of E given F is the probability that E occurs given that F has already occurred, and this is denoted by this. It means that like this: probability of E given that F has already observed. So that's the same thing. Sample space is all possible outcomes consistent with F. Okay, so since F is already observed, now your focus is on the possible outcomes that is now consistent with F, because you are not worried about other things from the sample space. So you have to focus on now S intersection F, because F is now already observed. So anything else apart from F that is in the F complement doesn't make sense. Okay, so you should focus on now all those outcomes that are consistent. So F intersection, but since F is already an event, so F is supposed to be a subset of S. Okay, so S intersection F must be F. Okay, unless someone gives you an because by our definition F, any event F is supposed to be a subset of S. Okay, if someone tells you something else which is not really an event but some arbitrary set that may be outside that, but then you will take an intersection and then make it relevant. So S intersection F. So event is all outcomes in E consistent with F. Now since you are considering probability of the event E given F, the only thing that matters in the output is also E intersection with F. Anything that is not intersecting with F is now no longer valid because you are asking for an event E where you are already given that F has observed. If it so happens that E has nothing to do with F, then it's a different thing. But and also, yeah, so E is equal to F, then there is nothing here again anymore because E intersection F, if F is same as E, then it's not really like conditional. So F has to be a bit different from E so that the conditional is changes, right? So E intersection F, so you should always look for now the outcomes that is now consistent with F. You cannot take anything else now. So with equally likely outcomes, the way we define is this ratio that we define here. Okay, so the probability of E given F can be taken as the ratio like this. Okay, so S intersection F, I am assuming that F is an event. So if F is an event, then F will be a subset of S. So hence I can write like this. Okay. So one way to do compute conditional probability is like this, and this is what we did in the previous slide. If you think of E intersection F, we did, and then we could have done directly by this. Okay, E intersection F divided. But here what I have defined is like really in the using the probability as well, right? So here, because I knew that the sample space is the same for both, so they gets cancelled out. Okay, so one way, another way is like you define the probability ratios, but here what we have defined is the ratio of the cardinality of E and F. Okay, so okay. And but this is the ratio thing is good when you have like equally likely outcomes. Okay, so that's something you should remember. There is an interpretation between what we have. Probability of E given F is probability of E intersection F divided by probability of F. There I don't assume equally likely, but here I assume equally likely. Then I'm taking the ratio. Okay. So these are the things we have to keep in mind. So if you can start doing conditional probability now, given that you know the counting and you can count E intersection F, you can count F. Okay. So this way you can. So this is a picture where we can understand graphically what is happening with the conditional probability. So what is probability of E, right? So probability of E here, so this is the red thing, is the conditional probability, is the E event. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so cardinality of E is 8, and how many are there? So I think it's 50 here. Okay, the total number of these cells are like 50. I'm not sure. Okay, maybe 50 or something. Okay. Okay, so in this case, probability of E is 8 by 50. Okay, done. And yeah, so 8 by 50. Now I can ask conditional probability. So what is the probability of E given F? Okay, so if you are given E given F, then you have to do E intersection F in case of equally likely, right? So this is the formula. You can E given cardinality of E intersection F and cardinality of F. Okay, cardinality of E intersection F and cardinality of F. So E intersection F in this case is like 1, 2, 3, and F is how much? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I hope the answer is correct. Yeah, or 12 or 14. Okay, 14 actually. So 2 more was here. This is also part of F. Okay, so in case of equally likely, the way we compute is cardinality of E intersection F, and then divided by F. Equally likely, just divide by the cardinality. If not equally likely, then use the probability definition, E intersection F. Okay, we will come to the. I think I jumped again a little bit ahead, and I went ahead but actually I should discuss this a bit later. Okay, you can focus on this definition right now. Okay, so this is conditional probability. Is very important, very important topic in probability, because many things happen with conditions, and this will lead us to Bayes rule. Bayes rule is one of the key in modern day machine learning. The way you model things with respect to data and conditions involved and so on. We will have some opportunity to do some applications. So let's see. Okay, so first application, let us say spam emails. Okay, so let us consider this. Okay, so email spam where conditional probability is useful. So let us see this. 24 emails are sent. Okay, let us say 24 emails are sent. 6 each to 4 users. Okay, 6 each to 4 users. So let us say I have user 1, user 2, user 3. Okay, so user 1, user 2, user 3, user 4. So 24 emails are there, 24 emails. So we just write all the important information here. 24 emails are there, and 6 each to 4 users. So 6 each, let us distribute 6 each to 4 users. 10 of the 24 emails are spam. Okay, so 10 out of the 24 are spam. Okay, and all possible outcomes are equally likely. Okay, so this is hinting us that we may use that ratio definition, right? Okay, now let the event E be that the user 1 receives 3 spam emails. So let us say the user 1 receives 3 spam emails. Okay, so now the question is, what is the probability? So what is the probability that, so what is the probability of that? Okay, so what is the probability of that the user 1 receives 3 spam emails? Okay, so what do you think about this problem, right? So how do you go about this problem? Okay, 6 emails to 4 users, and now you are talking about what is the probability that user 1 received 3 spam emails? So it should be a counting problem, right? It should be essentially it's a counting problem. Like what are the ways user 1 is going to receive 6 emails, and out of these 6 emails, what are the ways user 1 is going to receive 3 spams, right? What are the ways it's going to receive 3 spams, and what is there in the sample space, right? So what is there in the sample space? So all this. So tell me what you think. So tell me about your answer, and then I can look at the chat. Okay. So let me check here the chat. I hope you are okay with that. Yeah. So Mehul replied 10C3, 14C3, 24C6. Pranjal replied 10C3, 14C3, 24C6. Okay, so 2 people replied. Okay, and there are 3 likes over there. So liking is easy. Okay, so yeah, some other are coming. Suyas is coming with the same answer. Yeah, Suyas is coming with the same answer and so on. Yeah. So yeah, so the answer is right. It's about it's about what are the ways, like, look, user 1 is receiving 6 emails. Now the first question is like, what is there in the user 1 sample space? Right, user 1 is receiving 6 emails. So and since we are focusing only on the user 1, the other guys don't show up in the sample space. Okay, our focus is here. So what we are asking for is how many ways user 1 will receive the 3 spam emails. So the probability of the event, we can vaguely write this as number of ways user 1 receive number of ways 3 emails like the 3 spam emails come. Okay, so 3 spams. And the number of ways the user 1 receives emails. Number of emails. Oops. Number of ways the user 1 receives emails, right? So this will be how much, right? So this will be how much. So as some of you have pointed out, so there are like, okay, there are 6 places. So how many ways like I can receive the 3 spam emails, right? How many ways I can receive the 3 spam emails, right? And there are spam emails and there are non-spam emails also, right? So it turns out that I will 10C3. Okay, so because 10 out of the 24 emails are spam, so it's like 10C3. Okay, and then remaining ones are non-spam, so it's like 14C3. Okay, and then number of emails, number of ways I can receive the 6. So that will be like 24, total are 24 and 24C6. Okay, so this is via counting, right? So this is how I will so this is what is the probability here. So user 1 receives 3 spam emails. Okay, so out of 10 number of ways the 3 can come, 3 can be chosen. Okay, so that's 10C3, and then remaining 3 out of the 14, the number of ways it can be chosen, because we are talking about exactly 3, right? So this is, so we are not talking about, so this is like exactly 3 spam emails, right? So, and it doesn't matter ordering here, right? So you can fix these guys, right? These guys for spam and these guys for not spam. Okay, so now you are asking how many ways I can pick spam. So there are like 10 out of 24 are spam, so it's like 10C3 because it's exactly right. So I should now pick other as non-spam. So it should come from the other pool, which is the 14 of them are non-spam. So how many ways I can pick 3 non-spam, exactly 3 non-spam, because total I should have exactly 3 spam. This means that I should have exactly 3 non-spam. So exactly 3 non-spam, how many ways I can choose? So that should be 14 out of 3. And how many possible combinations are there? Because this could be anywhere, like, okay. So number of possibilities, this comes from the product rule. So 3 of the spams, 3 of the non-spams. Number of ways I make a product. So that there is all possible combination I get. So that gives me a number of ways to get exactly three spams. Okay, so that's why most of you also answered the same thing. Okay, so so you see things boil down to counting a lot, and this is what is in my sample space, because these are the 6 emails I should receive. So there could be so many ways. 24 choose 6 ways to receive 6 emails. Okay. Okay, now let us go to the conditional probability. Okay, so now what happens when we are given a condition? Now for a condition, I need some condition which is itself an event. So let event F equals to user to receive 6 spam emails. Okay, so now what I am given is that user to receive 6 spam emails. So let us make picture again. So initially it's good to play with pictures if you are not comfortable. Oh, sorry, there are only 4. There are only 4 users, right? So 1, 2, 3, 4 users. And what you are given as an additional condition is that user 2 received 6 spam emails. So user 2 received all 6 spam emails. Okay, user 2 received all 6 spam emails. So user 2 has received all 6 spam emails. This is an additional condition given to you now. And others are receiving emails, but we don't know, nothing is told about others, like how many are spam or not spam. That is not told to you. But this guy user 2 you are given now. Now the question is, what is the probability of E given F, right? So what is the probability now? So what is the, in words, what does this mean? Okay, so probability that user 1, okay, user 1 receives exactly 3 emails, right? The event E remains the same, right? The probability that user 1 receives 3 spam emails given that user 2 received 6 spams. Okay, so now you think how your count will change now, because now user 2 has received, you are already given that user 2 has received 6 emails, right? User 2 has received 6 emails. So how will your count change, right? Earlier you did the counting. It's a matter of counting still, but you have to modify, right? So we can go with our usual IQ based counting based thing. So I'm sure now that 6 spams went there, right? 6 spams went there. So as if these 6 spam emails now can be like reduced from our initial email, the spam count. Okay, so earlier we were given that 10 of the 24 emails are spam. So now I'm already given that F has happened. So I can reduce the spam quota to start with. Okay, to start with. So a number of spams that I can consider now, because this guy has already information is gone. So there is nothing undeterministic about this person. So 10 minus 6, sorry, yeah, 10 minus 6. So 10 minus 6 spams. So there are like 4 spams now left for the pool, in the pool of the spam emails, from which the user 1 has to receive 3. Right. So user 1 has to receive, user 1 still have to receive exactly 3 because event E didn't change. So user 1 needs to receive 3. It can receive, there are 4 still emails, spam emails left. And so again, like we go by the previous logic, right? So there are 6 places. I mean, the previous logic doesn't change. Only thing is like now we are given a condition, so things will get modified a bit. Okay, so the number of ways I can pick spam for the user 1 would be like number of ways I can fill the 3, let us say 3 spam places will be for C3. Okay, will be for C3, and for the remaining places, the pool did not change, right? So the non-spams are still 14 for us because there was no condition given on the non-spam email. So this pool is intact. The 14 is the non-spam. So I still have the liberty to choose the remaining 3 out of 14. So that remains the same. But something changes in the denominator now because okay, let me check. Did you answer already, just to verify that some of you? Okay, good. Yeah, so you have, some of you have already got the answer. Okay, so it's good to have one step ahead of me. Then it means like you are really into things. So what you have replied, some of you, is that it will be 18. So do you understand why they changed this? Well, it's simple, right? Because this 6 is also again given to you, just like in the spam case. In the top case, you have only left with 4. Now in the global pool also, you are only left with 18 to choose from, because this guy is deterministic now. I mean, the information is already given to us, so that makes it 18. So 24 minus 6. The global pool should reduce, right? So this is 18. Okay, 24 minus 6, 18. And oh, sorry, this is, so this should be 6, right? Okay, you get the idea. Because I'm still choosing 6, right? The user 1 is still receiving 6, right? So the sample space is this. Okay. So you see how an additional information can change the probability. So this probability of E is now not the same as probability of E given F. Okay, so probability of E is not necessarily same as probability of E given F. Okay, but you can think of, you can again go ahead of me and you can think of cases where probability of E given F becomes equal to probability of E. Okay, so what could be the cases where, so at this point you may already start thinking about examples where you can make probability of E given F exactly equal to probability of E. Okay, so you can think about this already in advance. I have not talked about this. There is a concept called independence, but as I said, when you do maths, you don't have to go with the key terms. You could go it's very important to have intuition behind how things evolve. People make things precise and define, but that's the secondary thing. First thing is that whether you can develop intuitions behind things, right? So when will the conditional probability won't be same, or when it can be same? So these are the examples. It should be already ready in your head by now. Okay, with the intuition we have developed. Okay, let us go ahead. Now what I will define is something called law of total probability. Again, all these are intuitive things. We will see that you see that, okay, this is like like trivial things. Okay, so the way, a more general way to define conditional probability, like I already told in the beginning itself, is the probability of E given F is that you take the ratio probability of E intersection F divided by probability of F. And this general case does not assume equally likely outcomes. Okay, so in this case, you can have this thing. Someone gives me this, and then I take the ratio and done. The cases where you the cardinality based definitions, there we assumed equally likely. Okay, but here we are not assuming in this definition of the conditional probability, okay, because I am just directly dealing with the probability. So this has been already computed, assuming biasness, whatever is there, okay. So that's why I'm no longer bothered about outcomes are likely or not. In this here, we were using equally likely, okay. So a proper otherwise, yeah, it may lead to error. Okay, so so from here the conditional probability, let's see. Okay, so the conditional probability definition here, from here I can write P of E intersection F is equal to probability of F times probability of E intersection F. That is just implied from here. There's nothing more here. Now from this we can derive something called law of total probability. Law of total probability says the following: probability of E is probability of E given F times probability of F plus probability of E given F complement times probability of the F complement. Okay, so intuitively you can think why this could be true. Okay, you can think because you have taken the cases F and you have also taken the case F complement. Okay, so together this will lead you to probability of the event E itself. Okay, so let us prove this, and during the proof you get the answer to this. Okay, so let us see the proof of this. So let us write the first step. The first step is that we know that if F is an event, then F and F complement are disjoint, and F union F complement must be the whole sample space, right? So we observe that F and F complement are disjoint. Okay, that is F intersection with F complement is the empty set, and what we also know is that F union F complement must be the whole sample space. The second step in the proof is I can write E, so that is where the intuition plays the role, right? So E can be written as E intersection F, okay, union E intersection F complement. So that's just set theory. For any E and F, that holds, this result holds, right? So that's set theory result. Now we know that these guys are supposed to be mutually exclusive, okay, because here you are taking intersection with F, here you are taking intersection with F complement, so surely they are disjoint. Okay, so they will not intersect. E intersection F intersection with E intersection F complement must be empty. So this means that they are disjoint. Okay, so they are disjoint. So this means that from the additivity property we have seen in the law, in the axioms. So now we can write this as probability of E will be probability of E intersection F plus probability of E intersection F complement. Okay, so this is coming from the additivity. Okay, and now we know that probability of E intersection F can be given by the chain rule. So this star, so from star we have, okay, so this follows here. So E intersection F is probability of E given F, and then probability of F, and similarly you apply a star over this. So this is plus probability of E given F complement, probability of F complement. Okay, so this is the proof of the law of total probability. Okay, now compute probability of E from probability of E given F using probability tree. Okay, let us go see how we can solve problems the conditional probability problems using the tree, probability tree, that we have seen in the Galton board experiment. We have seen in couple of other like prisoner problem and the boxes problem and so on. So let us consider this experiment. Flip a fair coin. Okay, flip a fair coin. If heads, roll a fair 6-sided die. Else, roll a fair 3-sided die. Okay, so there is like some branching happening here. You can already see. So there are two things involved. Like there is a coin and then there is a die. Coin decides which die you are going to throw. So there are two types of die here: 6-sided one and 3-sided one. Okay, so if it comes out to be head, then you roll 6-sided die, and if it comes out to be tail, then you roll 3-sided die. Okay, that's the experiment. Now you win if you roll a 6. Okay, so I know that a roll of 6 can only happen from the 6-sided die, because 3-sided die at most I can go 3-sided die at the number at most I can go is 3, right? So what is the probability of winning? Okay, so what is your probability of winning? What is the probability that you roll a 6-sided die? Okay, that's the question here. So how can we solve this problem? Okay, how can we solve this problem using the probability tree diagram? Right. So the initial condition that we have is decided by the coin. Okay, so it's either heads or tails. The probability that I go here is half. Okay, and then so if it is head, then I roll a 6-sided die. So the possibilities that I can expect is 1, 2, 3, 4, 5, 6, and here the possibilities you have is 1, 2, 3. The output on the die. Okay, so these are outputs from the die. So this is from the 6-sided die, and this is from the 3-sided die. Right. So now, yeah. So what is the probability that you win? Well, the probability of you winning can only come from here, because 6 is appearing here only, right? So by the probability tree diagram, if you the only way you can win is that you follow this branch, and if you follow this branch, the probability of picking this branch is half. And furthermore, the probability that you will pick the probability of getting 6 out of these 6 possibilities is 1/6. Okay, so it's like 1/12. Okay, so that's the probability of winning. Okay. Okay. Now you can also compute this probability using total probability. So this is an example of application of total probability. So how can we do this using total probability? Okay, so how can we do this using total probability? Now let us systematically apply total probability here. So solution using total probability. Let us define the event. Define the events E to be, let us say, you win. Okay, so you know how to win, right? So you win when you can get a 6, and let us say F is that you flip a head. Okay, or you get a head after a flip. Okay, what we want is probability of win. Okay, which is nothing but probability of E. This is what we want. Okay, so now with this we can apply the law of total probability. Okay, in this case you can see that there were like 2 types of events, so we are able to apply total probability on 2 events. Okay, you can like generalize this, but here we can apply the total probability law. So the total probability, recall the total probability. So total probability, what does this say? So if I have to compute the event E, then this is probability of E given F, probability of F plus probability of E given F complement and probability of F complement. Okay, so this is what law of total probability. If we were supposed to use this, then we need to obtain these individual values, right? Apparently the tree-based approach was better. So depending on the problem at hand, you have to see tree-based approach is actually very powerful, but it is good when you have like binary choices. Usually if it grows into a lot, then again you are in a problem. So let us calculate these individual terms. So what is probability of E given F, right? So probability of E given F. So let us compute probability of E given F. So in words, what does this mean? What is the probability that I win? Okay, given that the head is flipped. Actually, here also little bit of probability tree diagram is helping us, right? Because this is the picture we have in hand. So given that head has happened, okay, given that head has happened, okay, now someone already told me that you are going this way, so I'm going to neglect this half because this is now deterministic now. So now it became deterministic. So it's like I'm going to this left branch with probability 1, right? Because it's given. Okay, so that's why this half will not be taken into account anymore. So the question is, what is the probability of winning given that head has happened in the coin toss? So with the probability 1, now I'm going in this branch, and the only thing left is what is the probability that I will win after I have come to this branch in a deterministic way. So this means that it's 1/6, right? So it's like 1/6. Okay, so you see how the things changed. Someone gave me a branch, like you go on a road and you ask for directions, right? So there are multiple directions one can go. But if someone tells you this direction, then your probability suddenly increases from 112 to 1/6 in this case, right? Because at least one way you got deterministic, right? So this became 1 in their case. Okay, and then what we need is probability of F. So probability of F is like, what is the probability of flipping a head? Well, this is a coin toss, so probability of getting a head is 1/2. And then what is the probability? So we are now defining getting all these terms, right? We just want to use total probability. That's the idea, right? So probability of E given F complement is what, right? So in words, what this is saying, what is the probability that you will win if the complement of F has happened? The complement of F is that you flip tail, right? So this is F complement, which means that you flip a tail. So it's saying if you flip a tail, what is the probability that you will win? Well, from the problem description itself, we know that if we go to this branch, so this is the tail branch, and we are given that someone gave you a wrong direction now, right? So you will definitely not find the thing you are looking for. So because the 6 is not here, I know for sure that the thing I'm looking for is not here. To win, I need a roll of 6, but 3-sided die will never produce a roll of 6 because it's only number from 1 to 3. So here I know that by this way I'm surely going to lose. So probability of finding a 6 along that branch is 0. Okay, and then probability of the F complement is half, because probability of the F complement is like probability of tail. Okay, probability of tail is same as the probability of head, so which is like half. You could also do 1 minus half. So it should be, it's the probability of complement is 1 minus probability of F, right? So again it will be 1 minus half, which is still half. Okay, so we have all the things that we need, and if you compute now probability of E, it will come out to be 1/12, which is 0.083. Okay, in numerics. Okay, so this is how total probability can be applied. Now let us see a problem of where conditional probability is important, and in particular what we are going to is so-called Bayes theorem. Okay, so Bayes theorem Bayes theorem is about it builds on the conditional probability and the chain rule and so on. Okay, so this can be applied to the spam emails and so on, but I think I'm running out of time for today.